Hello, and welcome to the Echostate Network, a machine learning approach. Machine learning is one of those things in science that everyone has at least heard of, and everyone probably has at least a vague understanding of what it is. I mean, the name is kind of self-explanatory, right? It's a machine learning, it's artificial intelligence, it's robots gaining sentience and rising up and killing all of us. Well, not quite. Machine learning is actually just a form of statistics. We apply what is called a machine learning algorithm to large sets of data that would normally be a nightmare to look through, but they become much more tractable through the algorithm. Don't let the wind get out of your sails too much, though, because it turns out that this branch of statistical analysis can do some really amazing things. Machine learning is a huge, multifaceted topic, and it would take a long time to introduce you to the entire field. So what I want to do in this podcast is laser focus on a specific topic in machine learning, which just so happens to be the focus of research that I took part in the University of Maryland's 2020 Training and Research Experiences in Nonlinear Dynamics, or TREND program. This topic is the Reservoir computer, which is a simpler and much faster version of the most famous machine learning algorithm, the neural network. Before we talk about that, though, we should talk about the basics of machine learning itself. What exactly are we doing in machine learning? Well, like all branches of science, the first thing that we need is a problem. And we want a problem that's some kind of difficult task that would be tough to get a computer to do directly. Some example tasks can be mundane, like filtering spam emails, or they can be exciting, like getting robot legs to walk without falling over. Or they can be morally shaky, like detecting a human face in a photograph. Now, I say these are hard problems to get a computer to do, but how do we know that they're hard? That is to say, how do we know when a problem is so tough that we need to resort to machine learning to solve it? Well, to know that, we need to know what computers are good at doing. And that's easy, because there's really only one thing that computers can do, which is getting told exactly what to do. If you can spell out exactly what you want a computer to do in the coding language that it can understand, then the computer will do exactly that, and it'll do it really fast and really well. What a computer can't do then is be creative. It can't do anything extra. It can't make a tough decision, and it can't do anything you don't tell it to do. That's why, for example, a computer can't easily filter spam emails. Not every spam email is exactly the same, and a computer can't easily make the creative decisions that are required to separate a regular email from a spam one. So, there's the kind of problem that we need to use machine learning for. Any problem where on-the-spot decisions are required. That is the first step of a machine learning algorithm, teaching the program to make creative decisions. This is called the training step in the algorithm, and it's where the statistical heavy lifting comes in. In order to train a machine, we need to get a lot of data about our task at hand for it to look through. How exactly the machine learns from this data varies based on which algorithm you're using, but it's pretty easy to get what's going on here conceptually. Think about what happens when you learn something. Your teacher shows you how to do it, but when you try yourself, you don't get it right the first time. Your teacher will then correct you on what you did wrong, and you'll try again, maybe getting it wrong another time. You repeat this process until you fully learn the topic, and if you're successful, you'll be able to use what you learn to a high degree of success. It's the same idea for a machine learning algorithm. It goes through each data point and tries to figure out the correct way to carry out the task, changing its strategy until it gets it right. After the training step in the algorithm comes the prediction step, where the algorithm actually does the task you want it to do without any outside help. This is the part where it filters those emails, where the robot legs walk, and where your camera recognizes that it's your face in the frame. If you did a good job training the machine, it will often be able to carry out the task surprisingly well. All machine learning algorithms follow this general scheme, but not all algorithms are equally effective. An important step in completing a task using machine learning is to figure out which algorithm is best suited for your scenario. With that, we can break from the general discussion of all machine learning algorithms and focus on some specific ones. As I said, we will build to discussing the reservoir computer. Before we get into that, though, I'll have to tell you about one of the most famous algorithms in machine learning, the neural network. Neural networks were designed in the image of the one thing we already know is good at learning, the human brain. In fact, neural networks and machine learning in general originates from a seminal work in neuroscience, Donald Hebb's 1949 book, The Organization of Behavior. In this text, Hebb theorizes that the brain is made of thousands of cells called neurons. Each neuron communicates with every other neuron via electrical signals. Hebb applies a general rule to these neurons, which is now known as Hebbs Rule. The more two neurons communicate with each other, the stronger the electric signal between them is. This rule establishes a scheme through which the brain learns. To see how this works, think about a kid trying to learn how to hold a pencil. When you give the pencil to them, a collection of neurons in their brain will fire, sending electric signals all around their brain in the pattern that will cause them to hold something. Once the signals have taken the correct path through the brain, they'll be sent down to the hand to hold the pencil. But holding a pencil isn't like holding most other things, and the kid will probably do it wrong the first time. So you correct the kid and get them to try again, and now their brain will fire off a new batch of signals. The signals that were successful in the first place, like the ones that tell the hand to move, will fire again, whereas signals that were not successful, like the ones that tell the hand to just wrap around the pencil, will not fire again. Each time a signal fires, it gets stronger, so the successful signals that fire over and over again will eventually become the only path that occurs when the kid picks up a pencil. At this point, the kid will have successfully learned how to hold a pencil, and they won't even have to think about it anytime they pick up a pencil in the future. Hebb probably didn't expect that this work would pioneer a new field of computer science. For about 50 years after it was published, Hebb's ideas were thrown around for their potential to create learning machines without too much success. In the 1990s, however, his idea would become an integral part of machine learning with the invention of the neural network. So, how exactly does a neural network function? For the most part, it works the same as Hebb's brain. In place of neurons, we create a collection of nodes, which can be thought of as a collection of boxes that contain connections to other boxes. Each of these nodes are connected to other nodes by a collection of numbers called weights. Each weight is between 0 and 1, where the number represents the strength of the connection. So, if the weight between two nodes is 0, it means the nodes are not connected and never interact with each other. If it's 1, it means the nodes are linked, and one node firing will always cause the other node to fire. So if you try to picture this in your head, you might be thinking of something that looks like a spider web, where you have a bunch of boxes connected to each other by lines, where the boxes are the nodes and the lines are the weights. That's close to what a neural network is, but it's actually missing something. It turns out that the structure of the network is crucial to making it work. Now, since I'm going to be talking about the shape that neural networks take, it will probably be helpful to actually see what this looks like. So, to see a visual representation of a neural network, you can click the link in the description of this podcast to see a poster created by my research partner, Joseph Harvey. Now that you're looking at this great visual aid, let me explain it to you. The nodes in a neural network are grouped in a series of layers, and signals jump from layer to layer. So you start with a group of nodes called the input layer. Each node in the input layer is connected via weights to every node in the next layer, which is called the first hidden layer. Likewise, every node in the first hidden layer is connected to every node in the next hidden layer. This goes on for however many hidden layers you want, until finally the nodes in the last hidden layer are connected to the nodes in the output layer. The output layer is the end game of the neural network. When it outputs a signal, that signal is the answer to the task that you gave the network. If you're so disposed, you can think of the structure of a neural network like a sandwich. You start with a piece of bread, which here is analogous to our input layer. Then you put a piece of meat on top of that bread. That's our first hidden layer, and it's connected to the piece of bread. Then, if you want, you could put a piece of lettuce, which is connected to the piece of meat below it. You can put as many or as few of these extra pieces as you want, just like how the number of hidden layers varies between problems. And then, to top it off, you add one last piece of bread, which is connected to the last hidden layer. That top piece of bread is our output layer in this analogy. So now we're 2 steps down into understanding neural networks. We know what they are and what they look like. But how do they work? Well, if you remember a few minutes ago, I said that every machine learning algorithm works in 2 steps. First, you have to train the algorithm, and then you have to predict with it. So how do we train a neural network? Again, it works about the same as Hebb's brain. Take a large amount of data about the task you want to complete and put it through the input layer of your neural network. The information will run through your neural network, each layer firing off specific nodes determined by those nodes' connection to the previous layer. Eventually, the information will reach the output layer, where the neural network tries to complete its task. Almost certainly, the network will do it wrong the first few times. So, to fix where the network is wrong, we compare the network's output to the correct solution of the problem, identifying where the network went right and where it went wrong. We then update the weights in the network. The nodes that we want to be connected will have their weights get closer to 1, and the nodes that we don't want to be connected will have their weights get closer to 0. This is analogous to the electric signals between neurons in the Hebbs brain getting stronger when their connection is found to correctly pick up a pencil. We repeat this process for every bit of training data that we have, updating the connections each and every time. Once the neural network has been trained and tested to an acceptable degree, it's ready to move on to the next phase, the prediction phase. Here, you put your information into the input layer, and the signal will follow the path developed in the training phase and output whatever comes from that path. This is analogous to the kid picking up the pencil correctly without even thinking about it. The network follows the path laid out for it and does the correct thing. Neural networks are powerful objects, and the things they can do are surprising and incredible. But of course, everything has some kind of drawback. The main drawback for a neural network is the amount of time they take to train. As I implied with my pencil example, once a network is trained, it can do its job really fast, as if it didn't even need to think about it. But that is not true for the training phase. In a network that is big enough to do its job well, there are a massive number of weights, which all have to be updated every time you feed in new training data. Furthermore, the math that you have to do to correctly update the weights is not easy and can take a computer a little while to do. This adds up, and it's not uncommon for training to take an entire day, if not more. This is a big deal for computer scientists because there's nothing worse than having to wait that long in order to test their code and get results. So of course, if you want to improve your neural network, the first thing to ask is how could we train them faster? So, a big problem with the computational efficiency of the neural network is the sheer amount of weights that you need to compute in each iteration. There are the input weights, which connect the input layer to the first hidden layer in the network. There are the hidden weights, which connect each individual hidden layer to the next hidden layer. And there are the output weights, which connect the last hidden layer to the output. A clear way to cut down on computation time would be to just compute fewer of these weights. Now, as a suggestive example, what if we just ignore the input and hidden weights? Then we would just have to compute the optimal output weights, and voila, we would get our results. This is the exact idea behind the main topic of this podcast, which can be called either the Echostate network or the Reservoir computer. These are both accurate descriptive names for the algorithm, so it's hard to choose. But the reason we call it a reservoir computer is because the first step in setting up this algorithm is creating a reservoir, which is just a collection of the input weights and hidden weights. Remember that the structure of a neural network is like a sandwich. Nodes connected as a sequential set of layers through which information flows in discrete steps between the input layer and the output layer. A reservoir computer, on the other hand, is like if you put the contents of the sandwich into a blender with the hidden nodes in a gross slurry between the input layer and the output layer. The nodes are not stacked, and any node in the reservoir can connect to any other node, including itself. Remember that the whole point of this algorithm is that we don't compute the input weights and the hidden weights. We just have them there to work with. So when we create the reservoir, we just put a random assortment of numbers in it, and we distribute those numbers on a bell curve centered around 0. Whatever. Now, training a reservoir computer like this is really easy. All that is done is see the path information moves through the reservoir and use that to compute the output weights. Furthermore, it turns out that you don't need to use tough math to compute the output weights. All it takes is simple linear regression. All told, it only takes a computer a few seconds to create and train a reservoir. This quick training produces a collection of output weights, which can then be used to compute the desired output in the prediction phase. At this point, any skeptical listeners out there might be feeling a little incredulous. I mean, if all along, all we had to do was compute the output weights and it worked perfectly fine, why did we ever even bother computing any of the other weights? Why are more typical neural networks ever even considered when there's such an easy shortcut? Well, like all mathematical shortcuts, the reservoir computer has some drawbacks and some conditions. The condition where the reservoir works gets to why the algorithm is also called an echostate network. The network will only work if it has something called the echostate property. A network has the echostate property when we can figure out the path that a signal will move through the reservoir based solely on the data that we input to the network. When this happens, we can say that the path that a signal moves through the reservoir echoes the input. This means that the actual structure of the network, the actual way that the neurons are connected to each other, does not determine the way that information will flow through the network. It's the input that does that. This is why we can fill the reservoir with random numbers as the input and hidden weights, because as long as the network has the echostate property, these weights don't actually determine the information flow. As it turns out, ensuring that a network has the echostate property is a simple task. I'm not going to get in how to do it because the math is a little bit beyond the scope of the podcast, but I bring it up to make the point that any network could be pretty easily made into an echostate network. So, given that, what makes us decide when to use a reservoir computer and what problems are they useful for solving? We can answer this question by considering another aspect of the echostate property, the idea of input forgetting. Now, I've already said that the echostate property allows us to know the path that information will flow based only on our inputs, but we can actually go even further than that. If we want to know the approximate path, all we need are the most recent inputs. The importance of older inputs in determining the path is small. Thus, we say that an echostate network is input forgetting. After a few more inputs are added, the original input you put in doesn't really matter. The idea of input forgetting gives us what kind of problems we can use echostate networks to solve. Any problem that is done in steps, where you can figure out the next step of the problem based only on the most recent ones. An example of such a problem is trying to predict the weather. The conditions of the weather change so quickly that it is best to use recent weather conditions to predict the future ones. If you tried to use weather from a month ago, you would be totally lost. This example actually gives us a whole field of problems that echostate networks are useful for solving. Chaos. A couple of examples of chaos are the weather, which I just mentioned, and the double pendulum, which you should totally look up on YouTube if you've never heard of. The idea of chaos is probably somewhat familiar to you. It is exemplified by the butterfly effect, which is an idea that has fully integrated itself into the popular imagination. The butterfly effect states that a butterfly flapping its wings in one part of the world could cause a chain reaction of weather events that ultimately results in a hurricane on the other side of the world. This idea gets to the heart of chaos. Very small changes cause big changes down the road. Because of the butterfly effect, chaos is very hard to work with. As it turns out, it's nearly impossible to solve problems exactly in chaos through known math techniques. But even if we try to find an approximate solution, the error that comes from the approximation will blow up as time goes on. Think of the initial minimal error as the butterfly flap, and the blown up error as the hurricane. Now, there are several different ways to approximate chaos, but the one that matters to us is, of course, the echostate network. So let's go through the process of getting an echostate network to predict something chaotic like the weather. First things first, we have to create our reservoir. Generally, the bigger the reservoir, the better the performance. So we can collect several thousand random input weights and several thousand random hidden weights to represent our reservoir. Next, we do the most important step in every machine learning algorithm. We train our network. To do this, we have to take a set of predetermined data about our system, which can consist of a series of points describing the weather, such as wind velocity, temperature, and humidity. Using this data, we can compute the path that information moves through the reservoir and the output weights, which will be computed so that we can closely predict what the weather will be like on the next step, given the wind velocity, temperature, and humidity at the current step. Once we've gotten through all the training data, we can get to the prediction phase of the network. This is where we're trying to get the network to actually guess what the weather will be like in the future. Here, our input will be the weather at a given time, and the computer will output its guess for what the weather will be like at the next time. Then we loop the output back and make it the input for the next step, which allows us to predict the weather at the time after that. We can continue this loop for as long as we want, predicting the system out to any time that we choose. Now that we can get an echostate network to predict chaos, we've just got one question. How good does it do? Well, remember that for a chaotic system, any small amount of error will blow up over time, meaning that we can never expect to predict the system for a super long time. That being said, though, if we set the parameters of the reservoir computer well, it turns out that we can accurately predict the system for a pretty impressive amount of time. However, the predictive power of the reservoir computer alone is not what makes it interesting to use it to predict chaos. If, again, you are able to properly tweak the parameters of the reservoir computer, you can begin to notice something interesting about the output. Even when it stops predicting the exact trajectory of the system, it still can predict the general pattern quite well. This is impressive when you realize that chaotic systems are not periodic, but also do not blow up to infinity. They just oscillate up and down in a manner that seems totally random. For example, think again about the weather. The temperature outside never blows up to infinity, but it also doesn't cycle around the same values in a predictable manner. It moves around in a difficult to predict, seemingly random way, and yet the reservoir can replicate the shape of this pattern. It's as if it has somehow tapped into the chaotic nature of the system. This aspect of the reservoir computer was the topic of research for the team I was in the University of Maryland's Trend program. In our research, we sought to better understand the conditions under which an echostate network can replicate a system's chaos. It is still, of course, an open question among scientists, and if we can obtain a better understanding of it, we may be able to get a better grasp on several real-world chaotic systems whose dynamics we know little about, and we may even better understand the inner workings of the reservoir computer itself. Machine learning is an active field with far-reaching applications, and we are still in a phase where it is relatively young. In this podcast, I've discussed only one branch of this still growing tree, being the neural network and its offshoot, the Echostate network. While the general neural network has several layers of complexity that I wasn't able to get into, the Echostate network really isn't that much more complicated than how it was presented here. That underlying simplicity, as well as the fact that it takes almost no time at all to run a program with an Echostate network, exemplifies the importance of this algorithm. Scientists like working with the simplest possible model where they can, and if we can gain an in-depth understanding of the capabilities of this and other simple algorithms, we will likely see machine learning grow to be even more dominant than it is today. Before I go, I have a few people I would like to thank. Firstly, I would like to thank the National Science Foundation and the University of Maryland for funding this podcast. I would also like to thank my partner, Joseph Harvey, who, again, made a poster about reservoir computers that you should look at, link in description. I'd also like to thank my mentors, Edward Ott, Michelle Gervin, Thomas Antonsen, Brian Hunt, and Alex Wickner for their invaluable guidance along this journey. I would also like to thank Daniel Serrano for all his help with the script, as well as every other student in the Trend program. Gavin Blair, John Blue, Emma Brand, Anthony Cho, Gavin Courtwright, Mary Flor Jacobo, Melissa Kistling, Ari Riggins, and Amber Rodriguez Alicia. Thank you for listening.